All right, let's introduce polar coordinates. They're actually a special case of parametric equations, as we'll see. So if you have a coordinate in the xy plane, so let me draw an xy plane. And let's suppose you have a point in the xy plane. So there's my point. There's the x-axis, there's a y-axis. There are two ways to start at 0, 0 and travel to the coordinate that you see. The first way is Cartesian coordinates. This is what you're most comfortable with so far, probably. So Cartesian coordinates say you start at 0, 0, you look east, you travel some distance in the x direction, then you turn 90 degrees, head straight up, and travel a distance in the y direction to get the xy coordinate. That's method one. You start looking east, you walk x units, then you turn 90 degrees, walk y units. Polar coordinates get to the same point in maybe a more efficient manner sometimes. It says start at 0, 0, look east, and then rotate an angle, theta, pointing in the direction you want to go. So rotate an angle, theta, and then look towards the point you want to visit. Then travel a distance r to get there. So you first rotate an angle, let's call it theta, and then walk a distance r to get to the point you like. Now, based on the picture, we have two basic facts about the relationship between x, y, r, and theta. Right triangle trigonometry tells us the value of x in terms of r and theta. X is r cosine theta. And y is r sine theta. Now, if r is a function of theta, then you have two parametric equations. These are your parametric equations. You have x is r cosine theta, y is r sine theta. Your parametric equations. You could now take derivatives. You could take second derivatives. You could find arc length of polar equations just writing down these two parametric equations. Let's do some examples to see what some polar equations might look like. So here's an example. What are these polar equations? Let's do three of them. How about A? Let's do r equals 2. Let's do B. R equals, B. R equals secant theta, which we know is 1 over cosine theta. And let's do the third one. R is, how about 2 cosine 2 theta? Okay, here's my answer for part A. This one's the easiest one to think about. If I plug in r equals 2 into my parametric equations, I get x is 2 cosine theta, y is 2 sine theta. And unless otherwise specified, the values of theta that I'm going to allow are in between 0 and 2 pi, because theta could be any angle between 0 and 2 pi. This describes a circle traced out in the counterclockwise direction of radius 2. You could also imagine that no matter what angle I'm at, no matter how much I rotate, I always travel a distance 2 away from 0, 0. Well, that describes a circle of radius 2. A circle of radius 2. Centered at 0, 0, traversed in the counterclockwise direction exactly once. Let's do B. So if I do B, my polar equation turns into a parametric equation, and I get x is, well, if r is 1 over cosine theta, x would just be 1, I guess, and y would be sine over cosine, which is tangent theta. Well, in this case, since secant is undefined when cosine is equal to 0, I guess I'm not implicitly allowing the values of theta that make cosine equaling 0. So what does this describe in parametric equations? It says that the x value of your parametric equation always has to equal 1. So here's my xy axes. There's the x value, x equals 1. I'm always at that coordinate. But tangent, if you think about the graph of tangent, let's say on the interval from negative pi over 2 to pi over 2, the graph of tangent starts like down at negative infinity and like goes up towards positive infinity. That means that the y-coordinate you can imagine as starting down at negative infinity and traveling up to positive infinity. So the y-coordinate goes like this. So I would say the polar equation, r is 1 over cosine theta, gives you a straight line at x equals 1 going up. Okay, let's do the last example. Let's do r is 2 cosine 2 theta. So these give me the parametric equations. 2 cosine 2 theta times cosine theta. Y is 2 cosine 2 theta times sine theta. The values of theta, 0 and 2 pi. So you could plot this parametric equation just by plugging in a bunch of different values for theta and connecting the dots, seeing what happens. But I'm going to think about it a little bit differently. I'm going to think about this one the same way that we started thinking about polar coordinates, by rotating. So here's my xy axis. There's 1, 2, -1, -2. Here's 1, 2, -1, -2. Okay. If theta is equal to 0, that means I don't rotate anything. Back in this picture, I'm facing east. If I'm just pointing east, then I travel a distance of 2 cosine 0. Cosine of 0 is 1. So here I am. This is my first value. That's when theta is equal to 0. I'm rotating 0 radians, and I travel a distance of 2. Now let's suppose I plug in pi over 2. Well, actually, how about pi over 4? So at pi over 4, I have r is 2 cosine, and if I plug in pi over 4 for theta, I think I get pi over 2. Now, cosine pi over 2 is 0. So at pi over 4, I'm right here. I rotate pi over 4 radians, so I'm at a 45-degree angle, and then I don't leave. I just stay at r equals 0. Actually, that didn't tell me much about what happens in the middle here, so why don't we try another value? Let's do theta equals pi over 8. So then r would be 2 cosine pi over 4. Cosine pi over 4 is root 2 over 2, so I think I'm at the square root of 2. That means if I rotate pi over 8 radians, I travel a distance of pi over 2, which may be about there. Let's plot another point. How about at theta equals, how about pi over 2? So r is equal to 2 cosine. If I plug in pi over 2 here, I get cosine pi, which is negative 2. All right, let's do this one. Let's do this one. This one's interesting. So it says, if I rotate an angle of pi over 2, so I start east, so I start pointing east, then I rotate pi over 2 radians. Now I'm pointing straight up. I walk a distance of negative 2. So I point straight up, but then r gives me negative 2, and I'm way down here at this value. Okay, I'm not going to plot a lot more points right now in this video, but you could. You could plot a bunch of different points, and what would happen is that you would trace out a curve that looks like this. So watch this. This is an interesting shape. So trace out a curve. So this is my value at theta equals pi over 2. You would get kind of like a flower shape. I don't know if this is a flower or not, but you get a nice pattern that looks like this. So that would be the graph of the polar equation 2 cosine 2 theta. Again, polar equations are special cases of parametric equations like this. In our next video, I'll use calculus to take derivatives, find tangent lines, find arc lengths of polar equations. All right, see you there.